In the next section in Chapter 6, we're going to look at triangles in particular. So we're going to steer away from just similar polygons and focus on triangles. And we're going to look at proving some triangles. Don't freak out. I know you hear the word proof and you automatically shut down, think, oh my gosh, this is going to be so difficult. But I can promise you that by the end of this, you're going to feel a little bit better about proofs. Recall the definition of similar polygons. Similar polygons are polygons for which all of the corresponding angles are congruent, all of the angles are congruent, and the corresponding sides are proportional. They are not congruent because these similar triangles are going to be blown up or shrunk down, but they are proportional. So we can write this representation down here. So we have all the angles in these two figures are congruent. A is congruent to D, B to E, and C to F. And then the side lengths AB is congruent, or rather, excuse me, I just made the mistake there. AB is not congruent, but rather AB is proportional to DE, so we can write a ratio. AB over DE should be the same as BC divided by EF, which should be the same as AC divided by DF. Again, just a reminder, the numerators all come from this first triangle. The denominators all from the second. It's important not to accidentally flip those around, but to keep them all together. In past chapters, we were taught how to prove that triangles were congruent, either with side, angle, side, 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 or hypotenuse, leg. But what I want to point out is that these were all used to prove triangle congruence. What we're going to look at today, and the focus of this whole section, is what we call angle-angle similarity postulate. This is to prove that triangles are similar, which is not the same as proving they are congruent. We cannot use angle-angle to prove congruence, but we must focus just on proving that there's some ratio between two figures. So what we start with is if two angles of a triangle are congruent to two angles of another, so we have K is congruent to Y, J is congruent to X, then we can state that these two triangles are congruent. So we can make a triangle congruence, or excuse me, a triangle similarity statement. Triangle KLJ is similar to triangle YZX. Notice how I used corresponding angles and lined them up. So K matches up with Y, L matches up with Z, and that's exactly what it says in my statement. J matches up with X. Let's move on to the example. We've got two triangles. Let's decide if they are similar. So we have to show that two of the angles are congruent to two of the other angles. In the second triangle, the largest one, I can find the measure of angle B. It's equal to, we know that the interior sum of angles in a triangle is 180, so we can subtract off 105 as well as subtracting off 30 and get that the measure of angle B is 45. Now 45 for B does not match up for the measure of angle E down here. And clearly, if we solve this one down here, the value of D is not going to be 30. So in this case, we have that no, these are not similar. So we cannot make a similarity statement. Now, notice how in this statement we have triangle ABC and triangle DEF. The reason I matched up B to E was the way that was written. B should match up with E if these are similar. I want you to go ahead and try number 2 on your own. Make sure you write it down and have it ready for the next class. I'm going to temporarily skip number 1. I'm going to let you try that on your own, but I'm going to show you how to do number 2, so hopefully you can go back and focus on number 1 to solve for it. In number 2, we are given that these two triangles are similar, which means that they should have the same congruent angle measures. So, as written, triangle ABC similar to DEF, that means that A should be congruent to D. So we should have 48 degrees here. Now, these are both given as 90-degree angles, so we can solve for the third angle. 180 degrees minus 90 minus 48 is equal to 42 degrees. So we can say that the measure of angle E and the measure of angle B is both 42 degrees. We found all three measures. Just a little hint for number 1, you do have an isosceles triangle, so you're going to have to use the property of isosceles triangle base angles to solve for the two congruent angles at the bases. Again, I'm skipping over number 1. I'm going to let you try that on your own, and I'm going to approach number 2 so that you can see how to first approach it, and you should be fine to solve this on your own. The similar triangles we have here are triangle UVW is similar to, I'm going to match up the corresponding angles, the congruent angles. So U is congruent to triangle X, V is congruent to Y, and lastly W and Z. So we can make our similarity statement. Now to solve for X, what we have to do is set up ratios to make a proportion, an equation relating the ratios. So it doesn't matter which way you do this. You can start with the larger triangle or the smaller. I'm going to focus on 3, which should be 3 over 5 is the ratio or the scale factor. So 3/5 should be equal to the ratio of any of the other two sides. And I have the side xy, which is x minus 4, divided by the side uv, which is x. Setting it up is always the hardest step. After that, cross multiplication, or what we've been calling the cross product. So we get 3x is equal to 5 times, I'm going to use parentheses because we have x minus 4, an expression that needs to be distributed to. So I can distribute the 5 to the x and the minus 4, and I get 5x minus 4 times 5 is 20 is equal to 3x. Subtract a 5x from both sides. 3x minus 5x is negative 2x is equal to minus 20. Solving for x, I can divide both sides by negative 2, and I get that x is equal to 10. X is 10, which means that uv is the value of x, which is 10, and xy is 10 minus 4, which is equal to 6. Taking a look at this picture, we first have to find the similar triangles. So we can start with the larger triangle, outlined here with the yellow, and the smaller triangle will be the second triangle. Now I'll outline it here in kind of a red color. Clearly, both of these triangles share this angle, angle A, and they both have a right angle, both angle C and angle E. So we can say that these are similar by angle, and we can make our similarity statement that triangle ABC is similar to triangle ADE. You go ahead and try A and B on your own. You might want to pause it at this point, answer those two, and then we'll move on from there. Now to solve for x, we have to set up the proportion. So what we look at is the smaller triangle in relation to the larger one. And what we can say is 3/5 is proportional to, now the larger triangle, the base is actually 3 plus x, and now that diagonal, the hypotenuse of this triangle, is going to be 5 plus 2.5. This is a bit larger of a problem. You can solve it that way, it's fine. But one thing that you can actually do that we'll look into next chapter as well is look at the ratio of the sides. So for example, we look at the ratio between 3 and x and 5 and 2.5 and set it up as a proportion, because they should be in the same ratio. So I'm going to write or here. We can do 3 divided by x is equal to 5 divided by 2.5. Again, just a ratio of the different sides, different pieces. I'm not necessarily taking the full base of triangle AED, but rather just taking this portion CE and BD, the extension from the smaller triangle. Now, I urge you to try it this way, the old method that we had, but I'm going to continue solving with the easier method. Taking the cross product, we get 3 times 2.5 is equal to 5x. 3 times 2.5 is 7.5, which is equal to 5x. Solving for x, we divide both sides by 5, and we get that x is equal to 1.5, which is the same as 3/2. For this last problem, we got a formal two-column proof, and we are given a triangle KIF, and we have that AS is parallel to IF. So I'm going to write that on the diagram. First thing you always want to do is label as much as possible. So I've got those parallel lines, and I'm going to extend them. You'll see why in a minute. It's just for a visual. So the easiest part of a two-column proof is what you start with. You start with triangle KIF, and you have that AS is parallel to IF. Now I didn't bother writing down triangle KIF because the important information is those parallel sides. So we can say that they're parallel because that was given. And what you should be thinking at this point is, what am I trying to do? Well, here we're trying to prove that these two triangles are similar. The smaller triangle is similar to the larger. So what we've got so far is probably somehow we're going to have to find two angles in each triangle that we could say are similar. And those are labeled, but we have to explain how those are congruent. So our end game here is to show that triangle KAS is indeed similar to triangle KIF by showing some congruent angles. And we know we want to show that by angle, angle. Now filling in the missing pieces. The reason is already given for you. If parallel lines are cut by a transversal, then corresponding angles are congruent. So here I've extended these lines to show that, well, these parallel lines are now cut by transversals. The first transversal is KI, so I can extend this here. And what we have is that angle 1 and angle 2 must be congruent because these are corresponding angles. Similarly, if we have our parallel lines and our transversal KF, then 3 and 4, those two angles, must also be congruent. So what I can write down here is that angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. That was a piece of cake because now we just showed two angles congruent in the triangles. That's all we needed. Once we have two congruencies, we're good to go. These are similar triangles. Angle, angle. That's it. So really, the goal here is just coming up with one of these. The difficult task is really just seeing what to use, what to dig up from previous chapters. And in this case, I'd say the hardest part is remembering that corresponding angles are congruent and actually seeing those in the two triangles given.